Hello students, welcome to my channel NCERT Unplugged, and in this video I explain you article number 5.2.2 bar magnet as an equivalent solenoid. We'll see that bar magnet, the magnetic field due to bar magnet is similar to that of an solenoid. Also, we'll derive the expression for magnetic field at the axial point of a solenoid, and we'll see that it is similar or it is same for that of a bar magnet. Okay, so let's start. So in the previous chapter we have explained how a current loop acts as a magnetic dipole. Okay, in the previous chapter we have seen that a current carrying loop, okay, if there is a current carrying loop, then there will be a magnetic moment associated with it. Okay, and it will act as a magnetic dipole. There will be two poles. The side where the current will be clockwise, it will act as south pole, and the side where current is anti-clock, it will act as north pole. So it will act as a magnetic dipole and there will be a magnetic moment associated with it. Okay, this was in chapter number 4. We mentioned Ampere hypothesis that all magnetic phenomena can be explained in terms of circulating current. Okay, so what we have seen in Ampere circular law, that the line integral of magnetic field is the mu naught times I current through the threading through the loop. Okay, so according to Ampere hypothesis, all the magnetic phenomena are due to electric circulating current. Okay, so now recall that the magnetic dipole moment M associated with a current loop was defined to be M is equal to NIA, where N is the number of turns in the loop, I is the current, N is the area vector. Okay, so what is the magnetic moment? Okay, magnetic moment of a loop, current carrying loop, that was M is equal to NIA. N is the number of turns in this coil. Okay, I is the current flowing in the coil. Okay, and A is the area of this coil, area vector. Okay, area vector of the coil. Okay, so this was the magnetic moment. In direction we can find out by, direction will be that of the area vector, and which can be find out by right hand rule. Okay, just curl your fingers in the direction of current, and the direction of thumb will give you the direction of magnetic moment. Okay, so this was in chapter number 4. You can see that. Now the resemblance of magnetic field lines for a bar magnet and a solenoid suggests that a bar magnet may be thought of as a large number of circulating currents in analogy with a solenoid. Okay, so the magnetic field lines of bar magnet and solenoid are similar. So we can think bar magnet as there are a large number of circulating currents in a bar magnet. Okay, cutting a bar magnet in half is like cutting a solenoid. Okay, we get two smaller solenoid with weaker magnetic properties. Okay, if we cut a solenoid, or if we cut a bar magnet, what we get? Two magnets with weaker magnetic properties. Okay, the field line remain continuous, emerging from one face of the solenoid entering into the other face. Okay, even then the field line will be continuous, it will emerge, okay, from one face. For bar magnet, emerge from this face and goes to this face. Okay, it is continuous. You already know this, north pole and south pole. Okay, direction inside is, the direction outside is from north to south, inside is south to north. So it is similar to the case of solenoid. Okay, now next we see the field lines remain continuous, emerging from one face. One can test this analogy by moving a small compass needle in the neighborhood of a bar magnet and a current carrying finite solenoid, and noting that deflection of the needle are similar in both cases. Okay, so if you move a needle in case of a bar magnet and a current carrying solenoid, what you see that the deflection is similar, suggesting the magnetic field is same in both the cases. Okay, now to make this analogy more firm, we calculate the axial field of a finite solenoid depicted in figure 5.4a. okay, there is a solenoid, you see. Okay, we'll find a magnetic field at the axial point of this solenoid. Okay, now we shall demonstrate that at large distances this axial point field resembles that of a bar magnet. Okay, for large distances the magnetic field will be same for that of a bar magnet. Okay, so let the solenoid of figure 5.4a consist of n turns per unit length. So what is n here? N is number of turns per unit length. Okay, so let its length be 12 and radius a. So you see the solenoid here, it is okay, it has the length of solenoid is 2L. Okay, from midpoint it is L here and L here. Okay, and its radius is what is the radius of this solenoid? A radius. Okay, and now after that we can evaluate the magnetic axial field at a point P at a distance r from the center O of the solenoid. Okay, so now we will find the magnetic field at a point at r distance from here. Okay, r distance from this midpoint of the solenoid. Okay, so for that what we consider a small element, this element. Okay, this ring will consider this current carrying ring. Okay, and because of this one turn we basically, okay, the number of turns in this small area, okay, in this small ring, because of that we'll find the magnetic field due to this point. Okay, and we'll integrate it for the whole length of the solenoid, and then we'll get the whole magnetic field to the solenoid. So to do this, consider circular current element of thickness dx of the solenoid at a distance x from its center. Okay, so what we did, we consider a circular element. This is the circular element dx, small circular element, which is at a distance x from the center of the solenoid. Okay, and we'll find the magnetic field due to this small element. Now in section 4.6 of the previous chapter, we have calculated the magnetic field on a axis of a circular current loop. Okay, so we have already done the magnetic field due to circular current loop at an axial point due to circular current carrying loop. So you can see that, and the expression for that, from that expression, the magnitude of the field at point due to circular element is, this is the expression we got in last chapter. Okay, you can see that article, and this is dB, small magnetic field due to that current element is mu naught n dx I a square to r minus x. Okay, here you see the distance is because r minus x is because this is from the distance. You see this was we have taken the current element x distance from the center of the solenoid, and the distance, this is r, so this distance will be what, this distance will be r minus x. Okay, that's why there is r minus x here, and plus a square. This you have to consider the last chapter and that particular article that you have mentioned, and you will see that the expression is more or less the same, but the only difference is r minus x. I already told you why there is r minus x. Okay, so now the magnitude. So what we do now, this is the, because of a small element, okay, small current element, for the whole solenoid we'll just integrate it. The magnitude of the total magnetic field is obtained by summing over all the element, in other words by integrating from x is equal to minus L to plus L. Okay, so we'll just integrate from, because we have taken from midpoint the distance r as from midpoint, so this will be from minus L and this will be plus L. So we'll just integrate it to obtain the total magnetic field. So now B will be this are constant, mu naught is constant, number of turns per unit turn is also a constant, current flowing is a constant. Okay, radius of the circle or the solenoid is a constant. So this comes out in outside of the integration. What remains is dx upon r minus x square plus a square whole to the power 3 by 2. Okay, so now this is integration, but this mathematics, basically this integration can be done by trigonometric substitution. This is how it is not necessary for our purpose. Okay, so it can be done by trigonometric substitution, but what we do in this, we will take the distance, the point where we have to find the magnetic field very far from the solenoid. Okay, then in that case what will happen, r will become very greater than a radius of the solenoid, and r is also become very greater than the length of the solenoid. Okay, then we can ignore them, the a and l, so it will come out approximately, because x is also very small. Okay, the distance will also become very small, because if l becomes small as compared to the radius and the distance from the point where we have find a magnetic field, then this x obviously becomes small. Okay, so we can neglect them. So what is left in here is, you see, r minus x whole square plus a square. So a square will be ignored, r minus x square 3 by 2. This will be 2 into 3 by 2, that is 3, r to the power 3, okay, r cube basically. So b is equal to what we get is mu naught ni a square 2r cube, and we can take out r cube outside of the integration. What remains is integration of just dx, limit minus l to L minus L to L, okay, and doing integration, so one integration is basically L, so what we get L minus minus L, so this is 2L, okay. So what this is the expression we get for a point far away, axial point far away from the solenoid, okay, mu naught ni 2 upon 2 times 2L a square by r cube, okay, where L is the length of the solenoid, A is the radius of the solenoid, R is the distance, or R is the distance from the solenoid to the point where we have to find the magnetic field, okay. Because the distance is very large, so it doesn't matter, we take it from center, or that L or A are just ignored, okay. So now don't the magnet of the magnetic moment of the solenoid is M is equal to M2A. So now we know what is the magnetic moment of solenoid. It is NIA, okay, NIA, number of turns per unit, total number of turns, I current, and area, okay. Here you see total number of turns is what, total number, n was what, small n was number of turns per unit length. What is the number of, suppose I say that the number of 2 in 1 centimeter, so 2 per centimeter, that will be the number of turns per unit length, okay. So for the whole solenoid, it is n is for unit length, suppose 1 centimeter, okay. For the whole solenoid, what will be it will be just multiply n into the whole length of the solenoid, that is n times 2n. So this becomes, okay, now this becomes, yeah, n into 2l, this is the total number of turns in the solenoid, okay. I is the current, and area is what, area of the solenoid is the area circle, basically this area, what is the area, the radius is a, so pi a square. So this is the magnetic moment, okay, and I can substitute here, okay. There is n, 2l, and pi a square, I can multiply and divide by pi, so what I get, this will become m. So when I put m here, so b is equal to mu naught 2m 4 pi r cube, okay. So this is the magnetic field for a axial point far away axial point from a solenoid, okay. This is also the far axial magnetic field or a bar magnet which one may obtain experiment. If we obtain expression for bar magnet, axial point magnetic field bar magnet experimentally, we'll get the same result. Even we'll do it later in this chapter by comparing it by electric dipole, okay. Then you will see that we'll get the same expression for magnetic field that we are getting for the solenoid, okay. So thus bar magnet and a solenoid produce similar magnetic field. The magnetic moment of a bar magnet is thus equal to the magnetic moment of a equivalent solenoid that produce the same magnetic field, okay. So the magnetic moment of bar magnet and magnetic moment of solenoid are same, they produce the same magnetic moment, okay, same magnetic field. Now some textbook assign a magnetic charge also called pole strength plus qm to the north pole and minus qm to the south pole of a bar magnet of length 2l and magnetic moment qm 2l, okay. So what is written in other textbooks also, but here it is avoided. You'll see the reason, because the reason is straightforward. You can see here magnetic monopole do not exist, it is not done here. But so what is their approach? It is, we'll take like we in a electric dipole we can take electric charges, okay. What is the electric charge? Minus q here plus q here. Similarly their magnetic moment is assigned, magnetic charge is assigned minus qm here, okay, and plus qm here, okay. We'll call them pole strength, okay. Magnetic charge also called pole strength, okay. And we'll calculate the magnetic dipole moment similar to that the electric dipole moment. What was electric dipole? P is equal to q into 2l. Here it will be what, the magnetic moment will be what, it will be q, that is qm, pole strength or magnetic charge times the distance between the two poles. Okay, so so similar to, if you recall from electric dipole what we did there. So the due to a single charge, what was the electric field at a distance r? This was that was 1 upon 4 pi epsilon naught, 1 upon 4 pi epsilon naught q upon r squared. This was electric field due to a single charge. Okay, similarly here it will be mu naught upon, for magnetic pole or single pole. Okay, single charge, magnetic charge or pole strength, mu naught upon 4 pi and qm upon 2 qm upon r square. Okay, only r square. So this will be the magnetic field due to a single magnetic pole. Okay, so then we can obtain the, because of the two charges. Okay, because of the whole dipole. This was for one, and because of two, and we can just do as we did in dipole case, electric field to dipole case. Similar steps are there. So but here it is avoided, as I already told you, because magnetic monopole we cannot separate magnetic poles. Okay, they will be in pairs always. There will be always my dipole, but in electric dipole that can be separated. The magnetic field due to the bar magnet is then obtained both for the axial and the equatorial case. Okay, after this, because of for single magnetic pole we have calculated this, so we can calculate for equatorial case and axial case. Same step as we did in electric charge dipole, but we have it is avoided here. Okay, the method is simple and appealing. However, magnetic monopole do not exist, and we have avoided this approach for this reason. Okay, so this I already told you. Okay, so I hope that this video was helpful to you in to understand this paragraph. If yes, hit the like button and subscribe to my channel for more such videos. I've already made this in Hindi, but now I am covering this in English also. Okay, the explanation was, I think, not very up to the mark in that, but in this I've tried to make raise my level. Okay, so and lastly, thanks for watching.